Last class was where we started talking about fractions, and we talked about fractions in terms of reducing them to simplest form. We talked about them for multiplication and division purposes, and multiplication and division for fractions is easier than addition and subtraction, in particular because all of your operations that you know and love, just multiplying across the top, multiplying across the bottom, those kinds of things are all the same. Adding and subtracting fractions is more complicated because we have to make sure the denominators match in order to do that. And so that's why it comes second. So today we're going to take a look at fractions again, but from a different perspective. So as I just said, in order to add fractions or subtract fractions, we have to have denominators that are equal. And I'm going to draw a picture of a couple of, well, I'll write it down first, but then we're going to draw a picture of a couple of fractions and why it is that we need them to be equal in order to add them. So we're going to add the fractions 1/3 and 1/2. And if you will, just make two fraction bars that are the same size and stack them on top of each other. So the first fraction is 1/3. So we're going to take the first box and we're going to split it into roughly 3 equal pieces. They don't have to be perfect, but close. And 1/3 means we've got to shade in one of them. The second fraction box is to split in half, and we will shade one of the 2 halves. So the problem with adding these together is that if I put them into the same diagram, the boxes that are shaded in are different sizes, right? So I can't neatly like take the shading of one and just shift it to the other one. And if I tried, it would look something like this, right? And it's sort of like not covering up all of that box at the end, but it's covering up part of it. And to know exactly how much of it covers up is not a direct observable trait. These aren't terrible ones to do, but the more complicated the fractions, the harder it is to observe. So what we need to be able to do is we need to be able to make those boxes the same size. So we're going to take those same boxes, and we're going to consider adding this 1/3 and 1/2. And since the boxes are not the same size, it didn't work. But what we can do is we can take the boxes and we can make them the same size. And here's how we do it. So the first bar that was in 1/3 can be split in half, each of the pieces. And again, it's not a perfect drawing, but there should be 6 boxes when I'm done that are approximately the same. And in the second box, I can take each of the 1/2 size boxes and split it into thirds. And again, it isn't perfect, but again, I have 6 boxes. So if I had drawn them perfectly, I would actually have boxes that are now the same size, right? And then we can imagine at that point taking my picture box and lining it up on top of this, and it lines up again. It's not perfect, but it should line up so that these 2 boxes line up right on top of that, and we have 5 boxes filled in. So I'm not doing a good job of putting these in the right spots. Oh, I think so. Actually, I think I'm missing a slide. Okay, I'll write it in for you. It says if we take 1/3 and divide by each box by in half, this is the one that's missing. We have 2 out of 6 shaded in. And take each, or take 1/2 and divide each box in thirds. We have 3/6. Now, the boxes are the same size. And my 1/3 plus my 1/2 equals 5/6. And picture-wise, if we take these images and we make them into the same box to the same size. We have visually 5, 6 like that. Sorry, don't know where the slide's missing, but it's missing. Okay, so the reason that we need to be able to have the boxes the same size is because it doesn't make sense not to. Right, so imagine that you have pizzas, for example, right? And you have large pizzas, and you have small pizzas, and you have medium-sized pizzas. None of the sizes of the pizzas are the same, right? The small pizza sizes are not the same as the big pizza sizes. So if you talked about how many slices of pizza you ate, you could talk about it like that, but the sizes aren't equal. So somebody who eats 2 slices of the large pizza does not eat the same amount as 2 slices of the small pizza. And then it also matters what sizes that the slices are split into. Do you get the large pizza and split it into 8 slices, or does it split into 12 slices? All those things affect the actual amount it is that you combine when you combine these pieces together. So we're going to take a look at some that already have the same denominator, and then we're going to shift to ones that don't and talk about how we deal with those. So example 1 has the same denominator. If the denominators are the same, it's very straightforward. We add across the top. So 1 plus 3 gives us 4. But the size of the denominator does not change. It does not become 10 plus 10 is 20, right? For the same reason that this picture over here, when I had 2 6 and I have 3 6, I end up with 5 6ths, right? The size of the box is still a 1/6 size. So on this one, the 10 stays the denominator, so we have 4 over 10. If this were in reduced form, like that were simple as it gets, we would be done, but it's not. 4 and 10 both divide by what?
2.
Yeah, they divide by 2. So if we have the ability to reduce something, we will reduce it. And this one gives me 2/5. Subtraction works exactly the same way. We subtract straight across the top. So since the 5's match on the bottom, 3 minus 1 is 2. And my denominator is 5, the same as it was before. And I promise you not all the answers are 2 over 5. But these both were. Now 2 over 5, just like on the last 2 over 5, is in simplest form, so there's no reducing to have happen on that one, right? Yeah. Okay, if the denominators don't match, like they didn't in my picture example, we need to find a way to make them match. And we're going to talk about one way to do that, that's the smallest denominator that you can get, which is the least common denominator. So we're looking at the 10 and the 18, and what we want to do is we want to break it down. And honestly, if they divide by something that's in common, we'd kind of like to divide them and break them down kind of in a factor tree by that value. For example, 10 and 18 are both divisible by 2, right? So this becomes 2 times 5, and this one becomes 2 times 9. The 2's match, but if we compare my 5 and my 9, they don't have anything else that they have in common, right? If they did, we'd break them down further. But to be perfectly honest, once they no longer have anything in common, the pieces that we've broken them into, we don't have to keep breaking it down. I know 9 breaks down into 3 times 3. And it doesn't hurt anything if you do that. You've just done more work than necessary. So once we get to the fact that the 2's match, what we do is we take the 5 and we take the 9 and we multiply them by the other piece. So this 9 gets multiplied by the 10. And the 5 gets multiplied by the 18. Now this problem doesn't ask me to add them together or even to change the fractions in their entirety. It just asks me to figure out what the common denominator is. And so what happens is when we multiply the 9 times the 10 or the 18 times the 5, if I've chosen the right values, through factoring, they should give me the same thing. So what is 9 times 10? 90. And either you know it, or you can do it, or you can grab your calculator. What is 18 times 5?
50?
Nope. It's 90, actually, as well. We hope they're the same. That's what we're shooting for each time. Okay, so I end up with the 90 and the 90. That is my least common denominator. So my least common denominator is 90. Okay, everybody good? Do you have a question, Jace? You sure?
Yeah.
Okay. All right, so the goal in getting the denominators to match is to be able to add and to subtract. So that's what we head to next. On this one, I have a 3 and a 6. 3 is prime, so it doesn't break down any at all, because, I mean, all you could do is write 3 times 1, and that's not any simpler. 6, however, does break down. How will 6 break down? Yeah, 3 and 2 or 2 and 3. So the 3's match, which means the piece that they don't have in common is the 2 that the 6 is being multiplied by, or being divided by. So I can use the 2 over here with this 3, and 2 times 3 as the denominator will be the 6 that the other one has. But in order to keep equivalent fractions, what we learned in the last section is that anything I do to the denominator, I have to do to the numerator. So I end up having 2 times 2, which is 4 over 6, plus the 1 over 6. And what is 4 over 6 plus 1 over 6?
5/6.
Yep, 5/6. Remember, add the top, leave the common denominator the same. That one was really nice because 6 is just a multiple of 3. I only had one piece that I had to work with. The next one's not quite as friendly, at least in some regards. 3's prime again. There's nothing I can do with it. But 8 doesn't divide by 3. I could write down that it's 4s and 2s, and that's fine, right? We could do that, and we could even write down that it's a couple more 2s, and so I have lots of 2s. But none of them match my 3, right? They're all completely different than the 3, which means my only common denominator that I can deal with is to actually take the 3 here times my 8, and then take all of this, which is equivalent to 8, times my 3. So my common denominator, 8 times 3, is what?
24.
It's 24. So they are both going to be a denominator of 24. But anything I do to the denominator, I have to equally do to the numerator. So on the top, I have 5 times 3, which is 15. And on the other one, I have 1 times 8, which is 8. So my subtraction goes, sort of like this in a wave. I've got 15 minus 8 now. And what is 15 minus 8? 7. 7 and 24, do they have anything in common? Nope. So we're done. 7 over 24. Okay, any questions on that one? Okay, this is our last one to do together. We have 2 over 7 and 1 over 9. 7's prime, kind of like the 3, so there's no breaking it down. The 9 will break down into 3 times 3, but again, it doesn't have a 7 in it. So it's a lot like the last problem. They don't share any common pieces, so we end up multiplying the 7 by the 9, top and bottom, and the 9 by the 7 on the top and the bottom. So what's my common denominator here? Somebody's whispering it. 63. Yep. How about the first numerator? 9 times 2. 18, yeah. But the second one, 1 times 7? 7. And then we have 18 minus 7, right? Which is 11 over 63, same denominator. Do 11 and 63 reduce? No, if it were 66 they would, right? 11 and 66 would, but 11 and 63 do not. And so then we're done. Okay, so that's the last one of those types. We have just a little bit more to do. We're going to talk about converting to a mixed number. Somebody was asking me about that. Gabe, you asked about that this morning, right? Earlier for their homework part. So we're going to talk about mixed numbers next. All right, so when we're talking about changing an improper fraction into a mixed number, it's valuable that you remember that the fraction bar really means division. So when I have 15 over 2, it really means 15 divided by 2. That's what it means. So if 15 divided by 2 is what I have, I just take 15 and divide it by 2. That's it. but you're going to show it on your paper. I'm looking at you, James, because I can tell you're going to be like, I don't want to show that. Yeah, I know. It's just annoying. We're not going to do it forever, but we're going to do it in this lesson. Okay, you're going to write down 15 divided by 2. How many times does 2 go into 15? 7. And 7 times 2 is 14. We subtract and we get a 1, right? So our whole number part is the number on top, 7. The remainder is the numerator of my fraction, and the original divisor is still the divisor of my fraction. So this is 7 1/2. Okay, so this is converting to a mixed number. Next, we're going to convert to a percent. So when possible, for converting to a percent, we will simply move decimals. If it becomes impossible to do so, we can do division. So if we're dividing by 100, it just means I'm moving the decimal. And in particular, because I have 2 zeros, the decimal moves 2 times. Okay? So 14% as a decimal, if you were looking at it in decimal form, would actually look like 0.14. That's what I mean by moving it. If it's already written over 100, percents are really easy because percent means per cent. How much is a cent? A penny, which is 1/100 of a dollar, right? There are 100 pennies in a dollar, yeah? So if we've got this written in over 100 form, then it really just means 14 over 100 is 14%. So there's not even any need to move anything if I recognize that if I've got it over 100, that's the form that's most closely related to percents anyway. It's 14%. Yep. One more. Let me throw this one in here. I've got this in my notes. It's not in your part. So let's do one more example on this part before we move to the next slide, so you can see what happens when it's not like that. We'll do 4 over 50, and then I'll do one more. All right, so if you have 4 over 50, obviously 50 is not 100, right? So it's not 4%. It's really easy to turn 50 to what? Into a 100, right? What would you need to do? Yeah, multiply them both by 2. So the 4 times 2 on top becomes 8. Bottom is 100. Once I have it in that something over 100 form, that's my answer. It's 8%. Most of the ones you are dealing with are going to be able to have the denominator changed into 100 using multiplication. But let me throw you in one example of what happens when it doesn't work, because it doesn't have to always be that way. Let's say, for instance, you had 3 over 8. I cannot multiply 8 by something and get 100, not just by a whole number anyway. It doesn't work like that. So in this case, this is the divide when necessary part of this description. So when you have 3 over 8, and you can't make 8 into 100 nicely, what you're going to do is much like we did over here with our mixed numbers, you're going to divide. So you have 3 divided by 8. Now clearly 8 doesn't go into 3 a whole number of times, so we automatically turn into some decimal forms. But 8 will go into 30. How many times? 3. 3 times 8 is 24. If we subtract, we have 6, and we bring it down. How many times will 8 go into 60? 7, yeah. 7 times 8 is 56. 60 minus 56 is 4. We're almost done. Bring another 0 down. How many times will 8 go into 40? 5. 5 times 8 is actually 40. So once I get to a remainder of 0, I would be done. This is the decimal approximation, 0.375. And then to turn it into a percentage, we would move the decimal point 2 places. 1, 2, and we would have 37.5%. Most of the ones you deal with are going to be able to be changed into 100s. But if they're not able to, or if you just like the division better, you can do that all the time. All right, last example, converting forms. We're going to take percents and turn them into fractions. So a percent means per 100. So when this says 12%, it means 12 over 100. So whatever the percent is, you just put it over 100. And then you reduce if it needs to be reduced. Can 12 and 100 both be divided by anything? Sure. What number? 2 will work. We'll start with 2. What's 12 divided by 2? 6. And 100 divided by 2? 50. Are 6 and 50 able to be reduced by anything? Yeah, 2 again. And if you had noticed it at first and saw that it was 4, you could have used it before, but not a problem. 6 divided by 2 is 3, and 50 divided by 2 is 25. And you're going to show some form of the reducing. My goal is not for you to put 12% into your calculator, hit the button that turns it into a percent. I'm not interested in what your calculator can do, but what you understand about conversions. Make sense?
Yep.
All right.